Hello everyone, I hope you had a good break. Please sit down. I got a short-term attention span exercise for you guys today. We're going to cover a lot of things in this video. Hopefully it's a useful video. Put it on 2 times speed. Look at the little chapters below to jump to things we're going to cover. First thing I'm going to do, since we've all had a break, we needed a little refresher on what we've covered. I'm just going to very quickly talk about what we've covered before the midterm, what we're going to look at before the end of the year or the end of the course. Then I'm going to cover chapter 7, which is energy. We're just going to talk about the main equations here. Here's a summary from the back of the chapter. And then we're going to apply those skills and solve a problem over here. So, thank you guys for joining me. What we did before was we looked at physics and measurement. This is like units, time, length, mass, things like this, little interesting things about physics. And then we covered motion in one dimension. There are some kinematic equations that you guys practice with. We learned about vectors, length, direction. You can describe 2D motion with vectors very nicely, and then you cover a bunch of problems with 2D motion. As you guys can see, these things get pretty complicated pretty quick, so it's good to practice them. Then we covered Newton's laws, F equals ma, and a bunch of different examples, so many different examples, blocks and pulleys and things like this, crazy stuff. Circular motion and other applications of Newton's laws. Again, F equals ma. You got things going in circles. You got cars sliding on ramps and stuff like this. So that is the stuff we covered before. Now you got to kind of take a pause, look at the future of the class, because we're going to shift gears. We learned about force and velocity and acceleration and all these kinds of things previously, but now you're going to learn about something new, so you have to take a break a little bit. And here we're going to learn about energy and work, kinetic energy, potential energy. We're going to learn about springs as well. Conservation of energy is also something interesting. So new words are introduced to you, new definitions, new ways to solve problems. But you still have to keep in mind the stuff you learned previously, because a lot of problems are going to look similar to a car sliding or a block sliding or a thing going in a circle. So you got to keep those things in mind. Anyway, we got 2 chapters on energy. Then you take a break again and shift gears and talk about linear momentum. So if you imagine a billiard table or things in space, you can talk about their momentum and figure out how they move and stuff like this. You don't just have to use Newton's laws. You don't have to just use energy. Now you can use momentum. Then you're going to talk about rotating rigid objects. Most of the time, this is when they introduce torque. Like if you're unscrewing a lug nut on your car, you apply torque with a wrench. So there's some problems related to that. Then you go back to momentum, angular momentum. First they introduce torque and rotating things, then they introduce angular momentum. Very similar type of stuff to linear momentum. You could use this to solve problems and get like velocity, acceleration, things like this from the problem. And then you, I think, end the class with static equilibrium. I don't think you guys cover elasticity. Static equilibrium is like, I don't know, I actually have no clue. Maybe you have a water and a leaf floating on the water. You kind of analyze it like this. But I don't think you learn too many new things. I think you normally rely on this chunk of stuff before the midterm. Energy and its conservation, and linear momentum and its conservation, and torque. I think that's enough stuff to solve all of the problems, and these last 2 chapters I don't think we cover. So that's a bit of a review of the year. It's good to check this stuff at a midterm point, and every week try to go and review this kind of stuff. Like you could just look at the chapters, look at some homework problems you did, and refresh your mind, because you don't want to forget the stuff that you covered in the midterm or before the midterm once you get to the final exam. Anyway, today we're going to talk about energy of a system. I'm not going to cover everything here, but I do like this thing at the end of the chapter, which covers most of the important things. So we're going to go through this stuff pretty quickly, and I'm going to share with you what's important. Don't stress about remembering this, but just keep in mind these equations that you see here and probably a few others are going to make an appearance quite frequently. So I don't know, maybe screenshot this and just look at it once before bed, once in the morning, once at lunch, and try to use some of these things in the homework. What I'm going to do today is just read this, share with you guys what I think, and then I'm going to apply exactly this stuff to the problem and try to solve it. And whatever I can't use or whatever I need to use that is not shown here, I'm going to make a note of that and be like, this is important. So let's start off. A system is most often a single particle, a collection of particles, or a region of space, and may vary in size and shape. A system boundary separates the system from the environment. Okay, so new definitions. Not too important, I don't think. The work, W, done on a system by an agent exerting a constant force F on the system is the product of the magnitude R of the displacement of the point of application of the force and the component F cosine theta of the force along the direction of the displacement delta R. Damn, that is a mouthful. That's a long sentence. But anyway, very quickly they introduced this new thing called work. It is a force times a distance, and this cosine theta takes the specific component of the force that points in the direction of the displacement. Don't stress about this if it doesn't make sense. Just keep in mind work is something that is introduced and it might be important. And the way you can make it is if you have a force and a displacement and sometimes an angle. So keep in mind these are things that you're probably going to see in a problem. Nice. If a varying force does work on a particle as the particle moves along the x-axis from xi to xf, the work done by the force on the particle is given by, and then here they give you another equation for work. Honestly, not too important. I'm just going to remember work equals force times distance, and that's something that's interesting that might make an appearance in the problems I'm seeing. But I'm not going to worry about this interval. Fx is the component of the force in the x direction. Cool. Kinetic energy of a particle of mass m moving with a speed v is this. Okay, cool. So we have work and we have kinetic energy. These are two things on the equation sheet. Nice. Scalar product, dot product of two vectors a and b is defined by this relationship. And there's a cosine theta here, and I remember there was also a cosine theta that appeared in the work equation. So they're introducing the dot product because work can be written as the dot product because it is a product of two vectors, the displacement and the force. If a particle of mass m is at a distance y above the Earth's surface, the gravitational potential energy of the particle Earth system is U subscript g mgy. The elastic potential energy stored in a spring of force constant k is us 1/2 kx squared. Okay, so two new things that are introduced to us. This u and some more symbols, but this is gravitational potential energy and elastic potential energy. So we learned about kinetic energy. Now we are learning about two different forms of potential energy, and we have learned about work. These are already so many new things, but keep these things in your mind. Work, kinetic, potential energy, and what else did we learn? Elastic and gravitational potential energy. Those are two different kinds. Maybe the scalar dot product if that's important, but this is already a lot of information, and we haven't looked at too much. We've just looked at the equations and the bolded words. If a force is conservative, honestly, I'm not going to read this. It's not important for today, but if you guys want, you can pause here and read it. Wikipedia search what is conservative and non-conservative forces. I don't think it'll be that important for the problems we're going to do, so I'm going to skip it. The total mechanical energy of a system is defined as the sum of the kinetic energy and the potential energy. So we're using something we learned before, the potential energy and the kinetic energy. We add them together and out comes this new thing called the total mechanical energy. So you add up kinetic, you add up potential. That is your total energy or total mechanical energy. Very cool, awesome little cute equation that you're going to see in many parts of physics. The work-kinetic energy theorem. This is a super important thing. Honestly, if F equals ma was the big bulk before the midterm, this thing is going to be the big bulk for this chapter and the next chapter as well. It says this theorem states that if work is done on a system by external forces, the only change in the system is in its speed. You could talk about this philosophically or just what it means for probably hours. We're going to just take this equation and be like, cool, I can plug in kinetic energies, I can plug in work, and I can get mass, velocity, I can work with all of these symbols here. Put it in the equation sheet, don't stress about it too much. Potential energy function, I'm also going to skip this, I don't think it's important. Unstable equilibrium, neutral equilibrium, static equilibrium, this I'm also going to skip. So the main things for me that I'm going to circle is this work. Let me put this in a bold thing. This work, this gravitational and elastic potential energy, this thing about kinetic energy, this thing about total energy, and this thing right here. So these are super important. This is 1, 2, 3, 4, 5 pieces of things I have to learn. I'm gonna just write this down on my hand or on a piece of paper in my pocket, look at it over and over, and these are the things that are gonna be applied to the homework, so you have to practice these and understand what they mean. If you don't know what they mean, the whole chapter is discussing them. Right now, we just want to quickly introduce ourselves to the equations of interest and attack a problem. So let's read this problem together. An inclined plane of angle theta has a spring of force constant K fastened securely at the bottom so that the spring is parallel to the surface. A block of mass m is placed on the plane at a distance d from the spring. From this position, the block is projected downwards toward the spring with a speed v, as shown in figure 7.63. By what distance is the spring compressed when the block momentarily comes to rest? Let's say we're reading this problem, and we would like to pull out some important information from it. First of all, here is the question. This is what I would start with. We need to answer this. So it says, by what distance is the spring compressed? Spring compressed equals question mark. I am looking for this. This is the most important thing of the problem. So I'm going to outline this. When the block momentarily comes to rest. Okay, maybe comes to rest is important as well. I'm going to underline that. Let's see what's given in the problem. So this is an inclined plane of angle theta. Automatically, I'm thinking of something like this with a block on it. This is the angle theta. Has a spring of force constant K fastened securely at the bottom. So we have a spring, right? It looks like this. And that is probably the spring that they're talking about in the problem. A block of mass m is placed on the plane at a distance d from the spring. Okay, so here is the spring and here is the block. This is a distance d and this guy has mass m. From this position, the block is projected downward toward the spring with a speed v, as shown in this figure. So I haven't seen this figure, but just from reading the problem, I've drawn this little picture. We're going to check this figure in a second and see how close I am. But one final thing is this block is sent down here with a speed v towards the spring. And this distance is what we're looking for. So let me find a picture of this. Alright guys, here's what the picture looks like. It looks pretty much the same as mine. There's a block. It is going down with this velocity v. Here is the distance from the block to where the spring starts. That's pretty important. So this is the distance, not the distance of this entire inclined plane. Here's the inclined plane. It has an angle theta, and k is the only thing I didn't write, which is the spring constant of this spring, k. We've seen this k before a few times in our equation sheet. It is over here in the elastic potential energy of a spring, and I think that's the only place it appears. Yeah, there's a capital K here, but that is for kinetic energy. So lowercase k, this is the only equation that includes that. More likely than not, I'm going to use this thing right here. And it's also inside this box, so who knows, maybe I'll have to use this thing right here too. But that's pretty cool. So we have this picture set up. Now what do we start? What do we start doing? Well, we read the problem, we drew a picture, and we outlined what is needed. Maybe if you're still just trying to write stuff, let's write what we have. We're given just symbols here, but we are given theta. We are given the distance there. We're given k. We're given the mass of the block, and v. We're given v. And we need distance. Spring is compressed. So this could be d or x, or sometimes they use delta x, or sometimes with these springs they might use delta r, but we're not going to look at that. So we're just going to look for a d or an x or an x, and we're not really sure what equation to use. But let's go grab some equations from here. So what's going to be important? For sure these two. So u equals mgy, u equals 1/2 kx squared. So I'm just going to write these down. Write them down in blue. So it said u of spring. What is this? This is the potential energy of a spring. 1/2 times the spring constant times x squared. And here is x, and this is actually pretty interesting. So we can kind of think about this. There's also a ug mgy. What does this mean? U of gravity equals m times g times y. Interesting. We don't have a y, but we have an m, and we know g is 9.8 meters per second squared if it's relating to gravity. So we have u. Where is u used? It is used, so there's a u right here, there's a u right here. The only equation it is used in is this one right here. This one. Total mechanical energy. Interesting. So I guess I'm going to write this equation down to E mech is equal to K plus U. So we have another set of equations, or not another set, but a different type. E mechanical is equal to kinetic energy plus potential energy. I'm just writing KE and PE, but potential energy normally they write as U, and kinetic normally they write as K. Sometimes you'll see kinetic energy as capital T, but not in this class. And then here there's a work kinetic energy theorem, but there's not, like, if we go back to work, there is a force and there is a displacement, this R, but I don't really see that in our problem. Maybe the displacement is what we're looking for, this distance the spring is compressed, but still I'm hesitant to use work because I don't see anything kind of related to work. Right, I see a K and then I'm kind of sent down this little rabbit hole here, so I'm gonna think about that, but maybe this might be useful here, this equation. We'll see. Okay, so what are these things that we're looking at? The potential energy of the spring, this is 1/2 times K, and then this X is actually the amount that this spring compresses. So if you have a spring here, and it starts like this, and it's holding some block, if you compress the spring, and it's over here, then this displacement over here, how much this has displaced, is our delta X that we're looking for. And also in here is some potential energy of the spring. So you displace it, and from this equation, you could see how much energy this creates. If you have a big K, it means your spring is really strong. It's super like rigid, and it takes a lot of energy to compress it. But then when you let it go, it gives you back a bunch of energy. And also here, if you compress it a little bit, the spring shoots back a little bit, but if you compress it a lot, the spring will shoot back a lot. So these things depend, the potential energy depends on these things. Cool. And this is the potential energy of gravity. You have your mass. If you have a super big thing, like, I don't know, a truck, and you drop it, that is releasing a bunch of energy. G is Earth, so if you go on a more big planet that pulls things down harder, I drop the same truck on Earth and I drop the same truck on this big planet with a big G, then the gravitational potential energy will bring the truck down with more energy. Makes sense. And Y is the height. If I drop the truck down from 1 inch compared to, I don't know, 1 kilometer, the 1 kilometer is going to have much more drastic effects. So that is where you get the potential energy due to gravity. So these are two equations that are important. This one is specifically related to the spring, and this one is specifically related to the height. Here, our block is a specific height up, so it has this mgy. And then it starts sliding down, and this mgy converts into kinetic energy. So originally the block is vibing up here, right? A distance y. What is this distance? I don't know, but we have a theta here and we have some distance here, so we can probably find this y using SOHCAHTOA. The block then slides down this way. Normally, if you see this sliding problem and you think about, oh, let me find the motion or the acceleration or something like this, you're going to start using Newton's law, which is what we learned before the midterm. But now we have energy, and since we are given a bunch of interesting things related to energy and springs, and we are in the energy and spring chapter, this is automatically something that is going to jump out at us. All right, so what do? We're just yapping over here. Here's what I will do. All right, guys, I'll be real. I went on a walk with my dogs and took a little break from the problem. I did this problem earlier today with some friends, and we went a different way about it. So we did not use this equation, but we instead used this work kinetic energy conservation equation. And because of that, I went through the book and found some missing information, specifically about the spring. This is the force that a spring exerts if it is extended by a distance x and it has a spring constant k. This is the work done by a spring. So if this is the force of a spring and this is the extension, you can find how much work the spring does by doing force times distance and integrating and some crazy shit like this. So you get up to this equation. I've seen even another one where here they have x final minus here they have x initial. I think that depends on the extension or the compression of the spring. I'm not too sure. But the reason I'm bringing this up is because I remember we used these two equations along with this equation to solve the problem. But what I pulled out of my equation sheets here is not work. It is just the potential and kinetic energy of the spring. So I started going down this path. It could be wrong because later we checked the solution with my friends after we found after we tried attacking the problem, and the solution also used this strategy here. But there's nothing really wrong with this method of thinking, I don't think. Like when you're doing a problem, you're not just instantly going to jump to the solution. So you want to kind of attempt different strategies. And if you see one strategy works and another doesn't, like for example, right now this work kinetic energy conservation theorem seems like the one that's going to work because it's in the solution manual. And this kinetic energy, mechanical energy conservation that I'm trying to use maybe is not the right thing. But you know what? I'm going to push through with the system. Here's what I have so far. At the initial position here, this guy has a potential energy of mgy, where y is this distance above the incline of angle theta. So this is its potential energy, and the kinetic energy originally I thought was 0 because I thought this thing started at rest, but it's not actually this. So I'm going to put an x through here. The kinetic energy is actually 1/2 mv squared. Because if you see in the problem, it says the block is projected downward with a speed of v. So originally, the block has this potential energy, but it's also being pushed a little bit. So it has this kinetic energy. So initially, you have this plus this as the total mechanical energy of the block here. It slides down. This potential energy converts into more kinetic energy, and then once it hits the spring here, the spring gets compressed. Some of this entire kinetic energy up here is converted into potential energy of the spring. How much? This is kind of an assumption I'm making. I'm going to say that E mechanical energy at top equals E mech at bottom. This is kind of like an energy conservation equation that I'm just pulling out of nowhere because I think it'll try to solve the problem. And what that looks like now is mgy plus 1/2 mv squared is equal to, well, at the bottom, this thing has no kinetic energy anymore. So k equals 0 or 1/2 mv squared. I just put those as the options. It does not equal 1/2 mv squared. Kinetic energy equals 0. And we know this because if we look here, by what distance is the spring compressed when the block momentarily comes to rest? So the block comes down here, it momentarily goes at rest, which means its velocity is 0, so its kinetic energy is 0. So here, if we want to do, this is the u part, this is the k part. This k part is 0, and the only u part is coming from the spring, 1/2 kx squared. And this we can say is u. Sorry, I should have put k over here. So what I'm doing here is using some kind of conservation of energy equation like this, which we haven't seen, which I don't know if it's going to work, but this is just what I'm thinking from the equation sheet. Potential energy, kinetic energy at the top is equal to potential energy plus kinetic energy at the bottom. Maybe this is somehow kind of similar to the work kinetic energy conservation equation. I'm not sure. I'm going to do some reading and try to figure it out. But right now, I'm just going to try this out and isolate for this guy. See what we get. So if I isolate for x, I'm going to do isolate for x squared. I have mgy plus 1/2 mv squared, and then I divide by 1/2 k. And then I can square root this entire thing to remove this square. And what do we have here? We have m, we have g, we don't have y. So I have to find y over here in terms of everything else. But here I have a theta, and here I know I have a distance. So I think I can do some SOHCAHTOA and find y in terms of d and theta. So let's draw another picture really quickly here. Let's say it goes like this, right? This is y, this is theta. The block starts here, and the spring is here. Let's draw the block also compressed here. So there is this distance here, d. So the reason I'm drawing d up to here is because that's where the spring originally was. That's the distance. But then the block compresses the spring by this delta x. So this entire distance here, we're going to call it delta x plus d. How do I know this is true? Well, when I first did the problem, I just used d. So I thought d was this entire distance here, and I had y in terms of d and theta. So you can see theta here is, you have the opposite, you have the hypotenuse, so that means sine of theta is equal to the opposite over the hypotenuse. So I can solve y is equal to d sine theta. This is how I solved the problem originally, and then we checked the solution and we saw that in fact here you have to account for this little delta x. So how do you learn this? You just solve the problem and you figure it out. So anyway, we have this delta x here, and from what we saw, sine theta is equal to opposite, which is y, over hypotenuse. So then here we have delta x plus d, and that is equal to y. So let me know if you guys have questions about where we got this from. And that should plug in nicely right over here. Then we have 1/2, that's okay. We have the mass, we have v, these are all given to us. We have 1/2 and we have k. Amazing. So what can we do here? Well, let's slide this over here maybe and simplify this a little bit. So we have a square root. I'm gonna cancel 1/2 here and just add a 1/2 here, if that's okay. And I'm gonna write everything on one line. So here I have, fuck it, I'm gonna do 1/2k like this. No need to do the 1. I'm gonna do m, g, and then here we have, oh damn, this is gonna mess us up. Here we have delta x inside this equation. So that is going to mess us up a bit because we're solving for delta x. Here we have an equation for delta x and there's delta x inside of it. So not good. And then here we have plus mv squared over k. Okay, interesting. Well, there's not a big problem here. I'm just going to square both sides again. And I have x squared over here is equal to, let's distribute everything here. mg, I'm going to replace the delta x with just x because we're solving for x. There's a sine theta here plus mgd sine theta here. And then both of these are over 2k. So I'm just going to put a 2k here. Put a 2k here. And let me move this. Let me resize this. Plus mv squared over k. Alright, now we have this equation. Oh my goodness, man, this is messy. How do we solve for x? So we have x squared minus mg sine theta over 2kx. This is not looking good. Plus mg d sine theta over 2k plus mv squared over k. This is not nice. Actually, here you have a minus and here you have a minus. So what did we do here? Well, this is the energy conservation equation. So we started from here. We plugged in potential energy at the top, kinetic energy at the top, kinetic energy at the bottom, potential energy at the bottom. And then we're isolating for x. And then we plug in this relationship to find what y equals. We get this, but it turns out that the delta x is inside here. We have to pull it out. So I'm going to move this square root back onto here. I get an x squared. And then this is now a quadratic equation, which is super annoying. So we have an x squared here and an x here, and a factor in front of the x. If you have mg theta, and here there's supposed to be a 2k, my bad. So if you have these numbers, this is just going to become something like x squared minus ax minus c is equal to 0. And then you can plug this into the quadratic formula and solve for x. That's kind of annoying, and I'm not even sure. Alright guys, so I did not want to go through that entire solution, but I pulled up the solution from the book right before they solved this quadratic equation, and it looks a little different. So here my x squared has nothing in front of it, but their x squared has a k2m. But here you can see I have k on all of my things. So I can multiply by k. These k's will get canceled, and I'm going to bring a k in front of here. Similarly, I can divide by 2m. So that's going to move this m here, this m here, and this m here, here. And I can divide it by 2, and there's going to be more factors of 2. So I can do that. Then there's a g sine theta here, x. If I cancel the m and I cancel the 2k, then I have g sine theta x. So this term looks the same as this term once I make the front of this term look like this, all right? And then here they have a minus, and here, all of this stuff inside these brackets, it does not depend on x. There's only one x here and an x squared over here. So this mg gets factored out. You have a d sine theta. Here's this d sine theta, and there's a g. This 2k gets factored out for this thing, right? And then here you have an mv squared. Here you have a v squared, but remember we factored out the m to put it in the front over here. And this k we also moved to put it over here. And then there's some 2's, there's some minus signs over here that you work out. So anyway, they get to this equation, which looks exactly the same as my equation here. And then they equate it for 0. And then this, like I said, it is a quadratic equation. So you could search up quadratic equation, find one that's like ax squared plus bx plus c equals 0, and then they give you where to put the a, where to put the c. Honestly, this is math. I don't want to practice math, and the main important thing is we were able to solve this problem. All right, plug this into symbol. I haven't figured out what's going on, but what we did was just pull out an equation. All right, I kind of pulled this out of my ass as well, but I did use the equations from the book. This one. I looked at the problem, thought conceptually what's going on, and then there's some missing info that I thought was interesting. So this missing info is how they do it in the solution. You could see their solution over here, and this is also some important stuff that I took note of. So as you guys can see, there's different ways of solving the problem, and there's things that are not at the back of the book that are still important. So go through the chapter. If you're interested in all of this stuff, what is the work-kinetic energy theorem? Why is this thing over here about the energies? Why does it work? They talk about it in the book, so just take a scan in the book. If you have any questions, please let me know, and I'll see you guys in the next one.